Welcome back, everybody. If you are following this on schedule, it is Wednesday, April 8th. So happy Wednesday. Also, happy Friday Eve for those of you who like that. Just like other videos, we have a wonderful special guest with us today, Miss Vampus.
Hi everyone, happy Wednesday, and we hope that everyone is doing well at this time, keeping safe and keeping healthy. All right, so we're going to jump right ahead and talk about our aim, which is what is equilibrium and how does it relate to Le Chatelier's principle? Okay, super fancy principle, it sounds like, but don't worry, we're going to take the time to break everything down so that you'll understand what it means.
Okay, so going first into irreversible and reversible reactions. Now, you've seen these words reversible and irreversible in your life before, but if we apply them to reactions, an irreversible reaction means that once you're going and you go forward, you can't go backwards. So if we have A plus B and you get C, that's it. Once C is made, you're done.
Right.
A reversible reaction, on the other hand, you
Right. It's basically it's one that the conversion of reactants to products and the conversion of products to reactants occur at the same time. So the fancy way of saying at the same time is simultaneously. Okay? So like Miss Scanlon had just said before, an irreversible reaction is just one way. But a reversible reaction, it can go one way forward and it could also go back. So how this is represented is with that double arrow that you see. Okay?
so we'll see this a lot go moving forward, but for this topic, we're talking about reversible reactions, so ones that can go both forward and backwards.
Right.
So when we're talking about equilibrium, it kind of looks like the word equal is in there, and that does play a part in some of this. The definition, if you were to look it up in, a boring chem book, would be that it would say that the rate or the speed of the forward reaction and the reverse reaction are happening at the same rate, meaning they're happening at the same speed.
Right.
And that the concentration, so the amount of stuff, stays constant. So if you think of it like this, if you set a treadmill at 5 miles an hour and you're running on it or walking at 3 miles an hour, you're not working at the same speeds. You will go flying off that treadmill. If the treadmill is set to 5 miles an hour and you run 7 miles an hour, that's not equal. You run straight into the treadmill and hurt yourself that way.
Mm-hmm.
But like Goldilocks and the Three Bears, you want to be just right. And if you set the treadmill to 5 and you're running at 5, both of you are working at the same speed. You're not going anywhere. That's what equal rate means. Same speed forward, same speed backwards. Now, one of the last things here is your concentration is constant. So we like to say con, so like the can dance, but this is the con equilibrium dance. Concentrations are constant, meaning they don't change. So going back to that treadmill example, you don't magically have more people appear on the treadmill. There's one person, that one person is there for the entire thing. Concentrations stay the same, they are constant.
Good. So if you notice the second bullet, it says that it can only occur in a closed system. The reactants nor products can leave the system. Okay, and if you look at the diagram over here, it shows that this is a closed system, meaning nothing is like affecting the factors within the system right now. Okay, and that's what we mean by a closed system.
Nothing in, nothing out.
That's right. So if you see that there's like a total of 10 fish in there, those 10 fish, they can swim to either side of the tanks, right? Connected by that tube. but none will be added to it or taken away. This is called a closed system.
Okay. Moving forward, again, this kind of reiterates what we said in the last slide. If the forward reaction and the reverse reaction are equal, so in the graph you have on this slide, the forward reaction ends up slowing down, the reverse ends up speeding up to the point where they both are working at the same rate. And then the concentration graph is the other one. Once equilibrium is reached, the concentrations stop changing. They are constant. So concentrations constant, rates equal. This is a very, very, very important statement that you need to remember, and that is what equilibrium is describing.
What is that sentence again?
Rates are equal, concentrations are constant. That's everything, a lot of what you need to know about what equilibrium is, the definition of it.
So basically what we said on these two slides right here, that is super important, and you need to commit that to memory. And a lot of Regents questions, they will, when they're talking about this equilibrium, it will emphasize these 2 points.
Okay. Moving forward is there are a few different types of equilibrium. So the first is phase or physical equilibrium. So essentially what this means is that if you were to have, let's say, water as a solid and water as a liquid, it's bouncing in between those two phases back and forth. So the compound itself, you have water in the beginning, water at the end. The compound is not changing, but the phase is. So you're popping back and forth between solids and liquids. So you have the same amount, a constant concentrations of solids and liquids. And if we look at the next slide, that is what happens at these phase changes. So at these phase changes, these flat things on your heating cooling curves, that is where phase equilibrium happens.
Right. So just to reemphasize, nothing is changing except for the phase. Okay, so the compound or the chemical compound or the chemical structure of things remains the same. It's only the phase that is changing in this type of equilibrium.
So if we look at the picture, we have a closed beaker. We have water molecules as a liquid and then water molecules as a gas. And they're like, oh my god, I'm so happy they've evaporated, they're gone. But little do they know, they're in a closed system, they can't leave. They come back, they condense themselves back into a liquid.
Right.
Okay.
So
Next.
the type of equilibrium we're going to talk about is solution equilibrium. It's a saturated solution. A saturated solution is at equilibrium. The rate of dissolving equals the rate of recrystallization. What does that mean?
So if we think about it, dissolving is when something breaks up when it's in water. So the opposite of dissolving is recrystallization. So that kind of bounces back and forth. If we can even put a double arrow there to show equilibrium. So this isn't the most talked about one, but that is one that does pop up.
All right, moving forward, chemical equilibrium. It's when the rates of the forward and reverse reactions are equal in a chemical reaction. So this one, yeah, we talked about the phase equilibrium, right? So we have a compound that bounces back and forth between phases. With a chemical equilibrium, we're not talking about the phase changes, but we're talking about Ms. Scanlon, go ahead.
We're talking about the actual compounds. So in this example, which I've just arrowed and circled, we're starting with N2 and H2, and then we're producing NH3. So in a closed system, the reactants make the products, but then you can also work backwards, and so technically the products make these reactants. So in the beginning, you have some set of stuff, and the products you have a different set of stuff. So in chemical equilibrium, you have different things that you're starting with and ending with. Okay. So moving forward, there was this dude named Chatelier, and he was French. And so he's studying these reactions, and he's putting them in these different conditions and seeing what he can do, and what he does, and looking at what he does and how it affects these reactions. So he's studying how, when these reactions at equilibrium are stressed out, how they change. So we like to use the term stress. That just means we're changing something. So the stresses that you'll see in reactions are changing concentration, so the amount of stuff, changing temperature, and changing pressure. So those are the stresses we're going to be talking about with Le Chatelier's principle.
So, like, when we're going to really just focus on concentration and temperature, with pressure, it gets a little bit, like, hairy, okay? But what we really want you to focus on is concentration and temperature right now, okay? And when we're about to put it all together in our next slide, we'll, like, stress that a little bit more.
Okay. So these are all the rules boiled down to one slide. So are you still confused at this point? Probably. Absolutely. Totally okay. So the next 2 days are geared just towards practice, but this gives you all the rules at once. Now, if we were to do this in class, it would have showed you the Shakira song Waka Waka, because there is a dance in there that kind of shows these shifts. So if we're looking at these bullet points, so the first one, if we're adding to the left, that means we shift towards the right. So if we're going to break that down, so we have the reaction A plus B gives you C plus D. And again, if I were you, write down left side and right side, because if you forget your lefts and your rights, something I do quite often, this would be a very silly reason to get a question wrong. So if you are adding, so at this point we're at equilibrium, we have that double-headed arrow. The speed of the forward and the reverse reaction are equal. So these two reactions are at equal strength. Neither one is stronger than the other.
Right.
But if we add stuff to the left-hand side, now the left-hand side is stronger. So now that since the left-hand side is stronger, it will push the reaction towards the right-hand side. That is what the shift means.
Right, and so that's what bullet 1 is talking about when we're, like, when you're looking at it, you're like, add to the left, shift to the right. Like, what does that even mean? This is what it means. We're looking at a chemical reaction, and when we're adding stuff to the left, it's going to shift to the right. So the stress, this is where the stresses, right, the sources of stress come in. And so, like we said earlier, those three stresses, concentration, temperature, and pressure, but we're really just, these bullets that we're talking about really just focus on concentration and temperature. So basically, if we're adding heat or temperature to the left, this reaction is going to shift to the right. So that's like one example.
Okay. So the next one, if you add to the right, so if we get rid of some of these pen markings here, so using the A plus B gives you C plus D example. So now if we're looking at that second bullet, if you add to the right-hand side, now the right-hand side is stronger. That means it's going to then push the reaction towards the left. And again, that's what this equilibrium means. And so there's a great practice sheet that you guys will work on tomorrow that kind of applies this.
Right.
The next one, if you remove from the left, you shift to the left. That means if you have A plus B gives you C plus D, if you're removing stuff from the left-hand side, so that this side, if you're removing some of that stuff, that means the right-hand side is now stronger. So if the right-hand side is stronger, that means you shift towards the left. Okay? And then oppositely speaking, if you remove from the right, you shift towards the right. So if we jump down to the very, very last bullet point, there's a quick thing you can use to kind of help you remember, and that is AATT. For you bio people, that kind of looks like a set of nucleotides. It is not. But what AATT stands for, you add away, and then you can take towards. So if you're adding to one side, you move away from that one side. If you take from a specific side, you move towards what you just took from. And again, this will make more sense when you jump into practice tomorrow. Now, if we're looking at the pressure one, pressure only affects gases. Now, with that, if you increase pressure, you're moving to the side with the least moles of gas. So that's when you have to look into these coefficients. And the side with, when you increase pressure, you go to the side with the least amount of gas. If you decrease pressure, you go to the side with the most amount of gas. Again, this will make more sense when we jump into practice tomorrow. The last thing to point out, and this is even going to be highlighted because it is super important. If you add a catalyst, that does not stress out the reaction. So it only speeds it up. It doesn't change these, it changes the speed of the reaction equally. So it changes the forward as much as it changes the reverse. It does not stress out the reaction. So if you want to shift it one way or the other, a catalyst does not do that.
Right.
So this
only what the catalyst does is just speeds up the reaction, doesn't change anything else.
Exactly. So just to kind of sum everything up, if you have a closed system and a stress happens, the reaction has to deal with that problem on its own and shift one way or the other to kind of relieve that stress. So if you're thinking about everybody in a classroom, if somebody walks in to stresses everybody out, you can't just get up and leave. You have to deal with your problems on your own, and that's what these reactions are doing, and that's what Le Chatelier's principle is kind of talking about. How do these reactions respond to being stressed out? How do they solve their problems? Okay, it's very dramatic being a chemical reaction.
Yes, they go through a lot of shifting, right?
Now, yes, a lot of shifting.
Just like us.
We have a lot of shifting to go through a lot of times. So, on that note, that is it for Le Chatelier's principle. The next 2 days are focused on practice, and then you guys have the Castle Learning due on whatever day it is due. Check the calendar. But we hope that is it. Have fun. Watch the Waka Waka video. It is a great song, regardless of if it helps you with the content. And have a wonderful day.
Have a good day, guys. Enjoy. Bye.
Bye.